My talk is on formalization. Um, this is the structure of the talk. I'm going to start with some background. I'm going to, although will turn into a research talk, I'm going to start off quite gently so that everyone is on board to know what we're talking about. So I'm going to give the sort of basics of the field at a sort of relatively at a sort of undergraduate level, and then we'll move into more advanced material, including some of my research later in the presentation. So let's start thinking about validity, a valid argument in natural language. That can be, when I say natural language, that doesn't have to be in everyday speech, although it can be. I'm thinking also about more technical areas of natural language, such as mathematics or science or the law. We think of validity in two ways. When we start teaching students what the notion of validity is, we typically tend to say one of two things, or maybe both. We say something, we give a modal characterization that an argument is logically valid if and only if it's impossible for the premises to be true and the conclusion false. And the natural question the natural follow-up question is, what kind of modality are we talking about when we say it's impossible for the premises to be true and the conclusion to be false? A second kind of characterization, rather different, is that we often give to beginning students, is that an argument is logically valid in virtue of its form. And now the question there is, what is an argument's form? And of course, another question you might ask is, how do these two characterizations, the modal and the formal characterization, relate to one another? Are they the same? They are clearly different, but are they the same in extensional terms? Do they come to the same thing? Should they be, or will they give rise to different extensional accounts of validity? Claim that according to one, some arguments are valid, according to another, some arguments, that same argument is not valid. The modal characterization faces the question, as I mentioned, of the nature of the modality, and an obvious thought is that the modality is logical. If we say that the modality is logical, if we say, to go back to the slide, that an argument is logically valid if and only if it's logically impossible for the premises to be true and the conclusion to be false, it seems like we haven't got very far. It seems like we're in a very tight circle defining logical validity in terms of logical possibility and logical impossibility. If we go for another type of modality, it seems like we might get the answer wrong. So think about metaphysical modality, which I will assume that the audience is broadly familiar with, but I'll give an example of that. That the problem with this characterization is that there seem to be all sorts of arguments that preserve truth as a matter of metaphysical necessity, but are not logical. For example, if you say the stuff in the glass is water, so the stuff in the glass is H2O. Now, on the standard sort of Kripkean assumptions due to Saul Kripke, that the glass is water, water is H2O is necessarily equivalent to stuff in the glass is water, excuse me, is necessarily equivalent to the stuff in the glass is H2O, because water is H2O is a necessary identity. So if we accept that, it follows that this argument is metaphysically necessary. It's metaphysically impossible for the premise to be true and the conclusion to be false. But yet it doesn't look like the argument is logically valid. It looks like a different kind of validity. You might question that, but this typically motivates the more usual contemporary approach that pursues the formal characterization. So we've got the modal characterization, the formal characterization. The formal characterization seems like it's more promising on the surface than the modal one, because the modal one is either circular, if you define the modality as logical, or it gets the modality wrong. It's either the wrong kind of modality, or if it's the right kind of modality, namely logical, it's circular. So the standard contemporary approach is that an argument is valid if and only if it has a form, all of whose instances are truth preserving. So let's have an example of that. The classic example is all humans are mortal, Socrates is human, so Socrates is mortal. So that has a logical form, it seems, given by all H's are M's, S is H, so S is M. And it looks like all arguments of that form are truth preserving. If the premises are true, then the conclusion must also be true. In contrast, every argument of the form A is water, so A is H2O, is truth preserving as well. But the form of the argument isn't a logical one. So you might ask a bit more generally, and a bit more, you might ask for some more precision here. What is it for a set of statements of natural language to logically imply another statement on this formal approach? I'm going to use English as my example throughout because this talk is in English, but it can be any natural language. And as I said, when I say natural language, I include technical parts of natural language. So what is it for a set of English statements? I'm going to call that big S, a set big S, to logically imply another English statement, which I'm going to call little s. Well, on the formal approach, what you do is you formalize big S and little s in your preferred logic. Call that preferred logic L, just to stay fairly general. If this gives us the formalization in L of big S, that's the set of L formalizations of each of the members of big S, and formalization in L of little s, the L formalization of the statement S. So I've got the subscript here, L. That's the formalization into a particular logic for particular formal language. And we've got big set S of a set of statements and little s, which is a statement which big S may or may not imply. So let's have an example. So big S is a set of statements, Anne is a woman and all women are mortal, just to vary it a little bit. And little s is Anne is mortal. Okay. And let's say that logic L is first order logic, also known as predicate logic. Okay. So how do we formalize Anne is a woman in first order logic? We would formalize that as WA. That's one formalization. How would we formalize the claim all women are mortal? For all x, if WX, then MX. Or, for all x, WX arrow MX, if you want to pronounce it that way. And then the formalization of the conclusion, Anne is mortal, would just be MA, capital M, little a. Okay. So that's the first step in the formal account. What you do is you formalize your English sentences, the premise set and the conclusion into your preferred logic, L. Now there's a second step in the standard formal contemporary account of logical validity or logical consequence. And here there's a sort of parting of ways, but by far the more standard approach is the model theoretic analysis, the model theoretic semantics. You write M double turnstile phi, M satisfies phi, whenever formal sentence phi is true in model M, i.e. M satisfies phi. And there's a technical definition of that, but for our purposes, it's not required. And then the argument is valid if and only if any model of the premise set formalization is a model of the conclusions of formalization. Okay. So in our example, if M satisfies WA and for all X, WX arrow MX, then it's got to satisfy the conclusion as well, MA. That's what it is for the argument to be valid. So remember, there's two steps. The first step, just to go back to that former slide, is to formalize the English argument. The English argument is Anne is a woman. In this example, Anne is a woman. All women are mortal. Therefore, Anne is mortal. The first step is to formalize those in your preferred logic. Let's say that's first order logic. The second step is to give an account of what it is for the premises, formalized premises to imply the formalized conclusion in the logic L. And the standard way of doing that is the model theoretic account. You say that any model that satisfies the premise set satisfies the conclusion. And to satisfy the premise set is just to satisfy each of the premises. That's to say each of the premises is true in the model. A slightly different way of doing the second step is to give a proof theoretic semantics. Is a proof theoretic approach, I should say. The proof theoretic version is instead of having double turnstile has single turnstile. So we can write that phi is derivable from gamma, gamma turnstile phi. Whenever formal sentence phi can be derived in the formal system for L. That could be a formal system, maybe L has several formal systems. Perhaps they're extensionally equivalent, they give you the same account of single turnstile from the premise set gamma. Okay, so on the proof theoretic account, the argument is valid, the English argument is valid, if and only if the conclusions formalization can be derived from the premise set, the formalization of the premise set. So in our example above, of Anne is a woman, all women are mortal, therefore Anne is mortal. The claim, if it is valid, then it must be that MA is derivable in the system for first order logic deductive system in question from WA and for all X, WX arrow MX. Okay. So just to summarize the standard approach, the standard way to think about logical validity in natural language is that an argument is valid if and only if it has a form, all of whose instances are truth preserving. And the thought is that an argument is valid by virtue of its logical form, and all arguments of that form are truth preserving, right? So to go back to the Socrates argument, all humans are mortal. Socrates is human, so Socrates is mortal. That's the English argument. We can have an intermediate column where we sort of we give the form. We go halfway to the formalization in the logic. All H's are M's, S is H, therefore S is M, and then the full formalization in first order logic. And if we have a model theoretic account, then we see that the formal conclusion, the conclusion of the formal argument, does follow from the premises of the formal argument that vindicates the validity of the English argument. Okay. And so more generally, if we let L be a logic or the logic, perhaps that correctly represents logical consequence. Double turnstile L is a semantic consequence relation. Single turnstile L is deductive consequence relation. And again, big S is a set of natural language sentences and little s a natural language sentence. Then the model theoretic analysis tells us that big S implies little s, if and only if the formalization in L of big S implies in L the formalization in L of little s, and then the proof theoretic analysis replaces a double turnstile with a single turnstile. Instead of talking about models, it does it in terms of derivability. Okay. Okay. So this was just this was background to make sure that everyone is on board, to give you a sort of introduction to the way that philosophical logicians think about validity in natural language, and a sort of template for how people go about things. Of course, there's lots of questions raised by the analysis so far. One question is, what is logic L? Right? Is there one such logic, or are there many logics? Could you get a different account if if you formalize in logic L1 and you give a certain semantics for L1, and you get one account if you get maybe you get another account if you use logic L2, you formalize in L2 and have a different semantics for L2. So that's one sort of question, and that's a question that I've discussed and others have discussed. And it's known as the monism versus pluralism debate in logic. So logical monism versus logical pluralism, whether there's one correct logic in one sense or many. Of course, there are as many mathematical logics as you like. Anyone can set up a mathematical system that has certain sort of generic features which make it a logic, and investigate that. And there's absolutely no denying that fact. The question is, what, for the purposes of applying logic, for thinking about, in this particular case, this particular application, the consequence relation in natural language, which is the correct logic to use for that, or is there more than one, or is there exactly one? A second question raised by the introduction that I gave you was whether we should give a model theoretic or a proof theoretic analysis. I mentioned we could do it using double turnstile or using single turnstile. And the third, more neglected question, which is my question today, is what in general is the formalization? What is this formalization function? So remember that common to both approaches, on the formal approach, the formal characterization of validity is the idea that you've got to formalize first. But what is formalization? How do you formalize? Okay, so I'm now going to move beyond the introduction and focus on formalization, and that's, as I said, is a key component to the notion of logical consequence, and that is the notion I want to focus on today, as you would expect, given the title of my talk. Okay. So to formalize is to turn a sentence of natural language, English, Mandarin, and so on, into a sentence of a formal language. For example, in propositional logic, we might formalize it's raining as P and it's raining or it's snowing as PVQ, or P or Q, sometimes pronounced. In first order logic, also known as predicate logic, we might formalize Anna is fair as FA and every woman is fair as for all X, WX arrow FX. And logicians are very good at formalizing. We're very adept at formalizing. And it's a skill we teach all our students. If you teach a first year or second year course, introductory course on logic, typically you will teach your students to formalize natural language sentences. You will teach them to formalize Anna is fair as FA or some equivalent, and every woman is fair as for all X, WX, conditional FX or some equivalent, perhaps using different vocabulary. Fine. There's that the fact that we all do it, of course, doesn't mean we know how to do it. Just because you know how to tie your shoelaces doesn't mean that you can theoretically describe what you do when you tie your shoelaces. So the question is, what criteria guide formalization? And logicians have not been very forthcoming on these criteria. Not a huge amount has been written on the criteria that guide formalization. Of course, I want to distinguish two senses of formalization. There's formalization in the narrow sense and formalization in the broad sense. There's a much broader sense of formalization in which formalize ideas or intuitions to make them clearer. And in this broader project, a good deal of interpretation may be involved. Okay, so for example, you might an example of that is a famous example of that is turning some of Brau's informal ideas into formal ones about intuitionistic mathematics and intuitionistic logic. Brau was not the one who formalized his ideas himself; it was his students and others, and that involves that kind of project is a broader one than the one I'm focusing on today. Of course, it involves formalization in the narrow sense, but it also involves a lot of interpretation and filling in of gaps and clarifying and reducing and taking what is essential and formalizing that in the narrow sense. So really the narrow sense of formalization I'm interested in are, here are some natural language sentences, here is a target logic, and now you've got to translate those very sentences into that logic. That's to say, formalize. So that's the sense of formalization I'm interested in. I recognize that there are other senses, including this broader sense, but the one I'm interested in is this narrow sense of translating from a natural language into a formal language in the way that logicians do in order to try and capture the notion of logical validity. Okay, so that's all broadly introductory. Let's move on to thinking about formalization as a map. So as the suffix, the part of at the end of the word indicates, formalization is a process. It's something you do with inputs and outputs. More precisely, we can think of formalization as a map that takes sentences. It's a placeholder notion of a language such as English to sentences of a language such as that of propositional logic or first order logic or some other logic. Okay. We can call the informal language E for English, but it doesn't have to be English, of course. It can be any natural language. We can call the formal language of logic L. And what should we call the formalization map? Well, we can think of it as a function from the set of sentences of E to the set of sentences of L. And the question is, what makes such a map a formalization? Now, you might say there's a sort of terminological hurdle to clear at this point. You might say, well, any such map is a formalization, as long as you've got any map from the set of sentences of English to the set of sentences of a formal language, that is a formalization. In the same way that you could say, suppose I want to translate from English into Mandarin, you could say any way of doing it, any way of mapping English sentences to sentences of Mandarin is a translation, however good or bad that map is. So there's sort of two ways of speaking, either an inclusive sense of formalization or a more a narrower sense, and it doesn't really matter. I'll try and we can sort of speak both ways. But let me try and indicate what I have in mind, and should be familiar to any teacher of logic. So suppose that you're teaching a first year, an introductory course on logic, and you've explained to students what propositional logic is, and you've explained to them, you've introduced them to first order logic as well. And then you ask them to formalize some sentences. So you might ask them to formalize Fido is a dog, and the sentence there's a dog. And you ask them to formalize those in different logics, in propositional logic and in first order logic. So suppose you get a student who gives you the following answers: Fido is a dog that formalizes P, there's a dog formalizes Q in propositional logic. And then in first order logic, they formalize Fido as a dog as FA, and there's a dog as there's an X such as FX. You think, great, this student has understood the exercise, and you tick it. You give it you check it, it's correct. They've understood how to formalize these simple sentences into these logics. On the other hand, suppose you get another student who formalizes things in the following way. Fido is a dog, they formalize in propositional logic as P double arrow, QVR. There's a dog as Q and R. Fido is a dog as for all x for all y, fx double arrow gy, and there's a dog as for all x, x equals x. Then you ask the student, that's on the surface, these seem flatly wrong. You ask the student if there's any sort of philosophical agenda behind these. Turns out there isn't. It's just wrong. The student has just got these formalizations wrong. You don't give them any marks, and you try and ask them to speak. You ask them to speak to the better student to try and see what the correct formalizations are. So I hope we can agree that we have this kind of working definition of a good formalization and a bad formalization, or if you like, just a formalization full stop versus something that's not a formalization or a non-acceptable one. Okay, so I said we're talking about English, but really we're not quite when we're thinking about what we're formalizing in natural language such as English or Mandarin. But actually, the thing that logicians are more interested in, they're more interested in cleaned up versions of natural language. So English has lots of ambiguities of different kinds. It has structural ambiguities, lexical ambiguity. So an example of a structural ambiguity is John likes American English speakers. Okay, so does John like speakers of the dialect of English that is American English, or does John like speakers of English who are also by nationality American? So that's just a simple example of an ambiguity. Logicians tend to think of the project of formalization as either revealing ambiguities of this kind, or effectively operating on sentences of a language that's cleaned up in certain ways. For example, in particular, cleaned up of ambiguities. Because this sort of sentence of English corresponds to two different senses, we can sort of disambiguate and then formalize those two disambiguations. There is no single formalization in, say, first order logic of that specific sentence that John likes American English speakers sentence, because it's ambiguous. There's on one way of understanding it, it has one formalization, and another way of understanding it, it has another formalization. Now, how much should we clean up English before we formalize it? That is actually rather contentious. Philosophers disagree about this, and they disagree about it, especially in the context of the monism versus pluralism debate. Some philosophers say, well, if we're going to make sense of vagueness in natural language, then we can't clean up English to make English a precise language before formalizing it, because we need to make sense. One of the things we need to make sense of in looking at logical consequence is vagueness, and therefore that might lead to a different kind of logic than it did if we were just thinking about precise language, such as the language of mathematics. So this is really a controversial topic. I'm not going to talk about that much in this talk. I just wanted to flag it as an issue. The other issue I want to flag on this particular slide in speaking about the language E is your interest might be in English as spoken today on the 25th of June 2025, maybe English as spoken by people in a particular location, a particular dialect. That seems a rather sort of parochial project, um, a sort of somewhat limited project. You might be there are all sorts of words that come in and out of the language. For example, words, technological words that would not have been were introduced in the language in the last few decades. So Victorians wouldn't understand the word DVD or a laptop or any computer related words. So what would a more ambitious project, it seems, is to think about the logic of meaningful any kind of meaningful discourse and not focus on a particular natural language, which is contingently what it is today. Okay, so these are sort of points, cautionary points that I want to flag about the language E, but they're not going to be hugely central to my talk. But I wanted to say a little bit about what the language that we're formalizing is. Right, now let's move on to the heart of the issue now. Let's think about the criteria of formalization. I've gone very slowly in the build-up to make sure that everyone is on board and not to lose people. We are going to speed up a little bit, but now I want to focus on the key issue of the criteria of formalization and what those are. And I'm going to mention three of them. So the three criteria I want to focus on and want to stress are the following: capturing implication, respecting grammar, semantic proximity. Those three. And I will explain slowly, and I hope patiently, what those three criteria are. And I'm going to judge the certain formalizations and certain logics according to these criteria. The sort of main structure of the talk will be to show that these three criteria are insufficient, to suggest quite strongly that those three criteria are insufficient and that we need a fourth criterion. Perhaps this fourth criterion should have been obvious all along, but I think it's quite interesting to see that it is needed, and I don't think it's sufficiently appreciated by logicians. Certainly speaking, personally, I hadn't appreciated it until I started thinking about this topic a few years ago. And so the part of the journey will be to get to this fourth criterion and explain why it's a key criterion for formalization. But first, before we do that, we've got to explain what the first three criteria are. What do I mean by capturing implication, respecting grammar, and semantic proximity? Okay, let's start with the first one then, capturing implication. Some sets of English sentences imply some other English sentences, okay? So for example, it seems like that Fido's a dog implies there is a dog, okay? So we've got an implication relation there. Others do not. For example, Fido's a dog does not logically imply there's a cat. Okay? So there are some implications between English sentences and others, or if you, more generally, some sets of English sentences and other English sentences. And in other cases, there is no such implication. So what we have in the case of English is we have an implicational network. Some sentences imply others, and whereas in some cases they do not. So the idea is that the better the formalization is, the more accurately it captures these implicational relations. Imagine your implicational network as a sort of graph theoretic structure in natural language in E, and then think about the implicational network of the formal language, which has some other sentences, and they imply one another or not. And the aim is, according to this criterion, the aim is to come up with an implicational structure in the formalization that mirrors the formalization, the implicational structure in the original natural language. What you're trying to do is you're trying to capture the implicational structure as closely as possible, perhaps perfectly if you can, of the original English natural language. Right. And when I say, again, to stress, when I say natural language, that it could include, for example, mathematics. So if you have some axioms implying a theorem in sort of natural language or natural language with mathematical terms, sort of the mathematics that you encounter in the classroom or the seminar room, which is not a formal language, what you want is you want your formal language to capture the fact that the axioms, the formal axioms, the formalization of the axioms implies the formalization of the theorems, given that it does the Informal axioms imply the informal theorems in informal, usual, everyday mathematics. Okay, that was the first criterion, and I'm going to come back to it, but I want to move on to the second criterion, which is that a formalization should respect the grammatical form of an English sentence as much as possible. So this is a very natural thought. Suppose you've got a very simple sentence, the cat sat on the mat. So the way we would formalize that is as the letter P, the single sentence letter P, or atom P. Suppose, on the other hand, that you had a more complex statement, such as the cat sat on the mat and it's raining or it's not raining. The formalization of that would be something like P and P wedge brackets QV not Q. But notice that the English sentences are logically equivalent because it's raining or it's not raining, assuming that's a tautology, the English sentences are logically equivalent. But they get different formalizations. They are formalized in a different way in the simple example because there's more, the formalization is constrained to respect grammatical structure. For example, if you had taught a class of students and you asked them to formalize the cat sat on the mat, and they said P and P and P and P and P 113 times, you'd say something's gone wrong. You want to capture the grammatical structure, and there's just one conjunct there. There's just one sentence. Okay, so the idea is that when we formalize, we try and respect grammar as well. The third criterion enjoins us to formalize an English sentence, little s, as a formal sentence sigma, if sigma may be interpreted so as to be as close in meaning to little s as possible. There's a quite a well-known textbook, dated now, but was quite well-known in the late 20th century by Benson Mates. And Benson Mates discusses this criterion. He puts it forward. He says, I'll read out the quote. To formulate precise and workable rules for symbolizing sentences, by symbolizing sentences, he means what I said call formalizing, right? So symbolization, it's the same thing, of the natural language is a hopeless task. Right. Notice that that's the task I'm embarked on today, and he's calling it a hopeless task. I hope to do a little better. Benson Mates continues. In the more complicated cases, at least we are reduced to giving the empty-sounding advice. Ask yourself what the natural language sentence means, and then try to find a sentence of the formal language L, which, relative to the given interpretation, has as nearly as possible the same meaning. Okay, so what you do is you take a natural language sentence, you formalize it. What the sentence you want to formalize it as is a formal sentence sigma, as I put it, such that when you reinterpret sigma, you give it an interpretation, you get as close to S, the original sentence, as possible. So the idea is somehow there's semantic space and there's relations of distance and semantic space. And some sentences can be closer in meaning to others. And what you're doing when you're formalizing is you want to pick a formal sentence such that under some interpretation, you can get as close in meaning, you can get back to the, or as close to the English original sentence as possible in that semantic space. That's the sort of picture. Okay. So I've just given you. I'll go back to the slides. The slide with the three criteria. I've given you three criteria for good formalization. What we're trying to do when we're trying to formalize. And these things have come up in the literature. The literature, I should stress, really really stresses the first criterion, capturing implication. Sometimes when you read some authors, they just talk about capturing implication as if it's the only thing that matters. As long as you capture the network of implications in your formal language of the original fragment of English or the whole of English, then you've done the job. Okay, that's what logicians aim to do. Okay, so what I want to do now is I want to test these three criteria with a case study, and I'm going to have the simplest possible case, propositional logic versus first order logic, and I'm going to see how they measure up against these criteria of formalization. Okay, and intuitively, we think that first order logic is a better formalizing tool than propositional logic, but it's not at all clear that it does better when judged according to these criteria. Okay, so that's the question. If you judge them against these criteria, which does better, propositional logic or first order logic? And I think it's the rather counterintuitive answer. This is the one I'm going to suggest here is that it's a tie. They do equally well. And I'm going to draw on some results from some papers of mine, some discussion of mine in these papers. I'll have a bibliography at the end for those who want it, but this is the papers are drawn from. The results are drawn from these papers. Okay, let's have a very simple example. These examples are taken from some logic books that, especially the second one, I think the first one, it comes from this sort of source, that motivate the move from propositional logic to first order logic. On the left hand, in the left-hand column, we've got some arguments. The first one is Bruin is a bear, therefore there's a bear. Now, if you formalize that in propositional logic, it looks like you've got P, therefore Q. Whereas if you formalize it in first order logic, you've got B, therefore there's an X such as BX. Okay, so the propositional formalization is invalid. The English argument looks like it's valid. The propositional formalization is invalid. The first formalization is valid because clearly any model in which the premise is true is a model in which the conclusion is true. Standard semantics for propositional for first order logic. Therefore, it looks like first order logic does a better job than propositional logic. Okay. Similarly, Zeno is a tortoise. All tortoises are toothless. Zeno is toothless. Therefore, the Zeno is toothless. This is an example taken from our the logic textbook that we use at Oxford when we're teaching introductory logic. P, Q, therefore R is the propositional formalization. The first order formalization is TO, 4LX, TX, arrow HX, therefore HO. Again, same story. We've got what is an English, a valid English argument. The propositional logic formalization is invalid, whereas the first order logic formalization is valid. So these are the examples that you typically give a few lectures into your introductory logic class, and you say, this is what motivates the move from propositional logic to first order logic or predicate logic. And then then the students are motivated to learn first order logic so that they can formalize a larger class of English arguments whose validity, it seems, doesn't turn on just propositional features, but on other features, where you've got to actually look at the structure of the sentence at the subsentential level. Okay, so these are the kind of simple motivating examples. However, let's imagine that you are a propositionalist. So let's imagine that you think that actually propositional logic is able to do all the formalizing work that you need it to do. Then you might think, hang on, you've been a bit unfair here. You've just given me a particular formalization propositional logic, but there could be others. So if we go back to the Bruin as a bear argument, you could formalize the premise as P, and you could formalize the conclusion as P or Q. If P is understood to mean that Bruin is a bear, Q could be understood that something other than Bruin is a bear. Likewise, with the Zeno is a tortoise argument, you could maybe formalize the second premise as P arrow Q and R arrow S, where the first premise says something like, if Zeno is a tortoise, then Zeno is toothless. And the other conjunct takes care of the other things other than Zeno. If they're tortoises, then they're toothless. So therefore, then you do get a valid argument in propositional logic. So it's not so much propositional logic that seems to be the problem here. It's the particular formalizations that we chose. Okay. Now, all logicians, any logician, I predict, who sees this will think that something's gone wrong here. They'll say, look, there's something wrong with these formalizations into propositional logic. You've done something dodgy going on. Okay. The first, how do we sort of analyze that sense of discomfort that we, I think, naturally feel as logicians here? The first thought is that they're quite unnatural in some way, these formalizations. The natural formalization of the first argument is the one we gave earlier, P therefore Q, and similarly the second one, the natural formalization is P, Q therefore R. The other sense is, well, hang on, okay, so you've come up with a sort of clever formalization here that will do the job, will preserve the validity. But how do you know that you can do that more generally? for a larger fragment of sentences. You've just got some toy cases here. Maybe these kind of tricks, you're going to run out of tricks with more sentences when you have a more complex implicational network and a larger number of sentences. So I think we can identify two sources of unease here, two objections, that there's a lack of generality in this approach and there's unnaturalness. So what I want to do now is I want to speak to these objections and consider whether the propositionalist, someone who thinks propositional logic is the correct way to formalize, can respond to them. So the first is the question of generality. Can the trick be played more generally? And the answer is yes. And you can prove something like this you can prove this using a technical result. I've applied it in a particular context. Other logicians, including Yerebek, have proved this in a more general way, in a proof theoretic way. His proof is in context are all very different from mine, clearly much earlier. But my interests are philosophical, so and semantic. So I've done it in a different way, and I think it has some interesting philosophical consequences. So we need some definitions. Suppose you've got two logic with respective sets of sentences, sentence L1 and sentence L2, and they've got two different consequence relations. You've got the consequence relation of L1 and the consequence relation of L2, double tensile L1 and double tensile L2. And then the map J from the set of sentences to L1 to the set of sentences of L2 is a conservative translation, or it's a faithful translation, just when for any gamma and delta, gamma is a subset of the sentences of L1 and delta is a sentence of L1, gamma implies delta in L1 if and only if J of gamma implies J of delta in L2. Okay? So the idea is that whenever you've got the consequence relation holds between a set and some sentences in L1, then the things that they are mapped to, if that consequence relation holds in L1, that it should hold the map. The sentences that are mapped to should have the same property, and if they don't if gamma doesn't entail delta in L1, then the sentences that are mapped to have the same property, namely J gamma does not entail J delta in L2. This notion of conservative translation is more usually applied in a sort of deductive context. Here I'm just taking it to be double tensile. Nothing really hinges on that, although the proofs we will give will be semantic. I will mention, but that's the more usual context, which I'm here adapting to a semantic one. Consequence embedding is when such a conservative translation is one-to-one or injective. In that case, what you do is what happens is that you've got a sort of mirror image of the implicational structure of L1 in L2. There may be other things going on, but you can embed it in L2. So you've got an implicational copy of L1 sits within L2. And if the conservative translation is bijective, then you've got a consequence, what I call a consequence isomorphism. Okay, a conservative translation that's also bijection. What you've got, what's going on is that the logics are, as far as implication goes, there may be all sorts of other difference, but as far as these implication relations go, are isomorphic. Okay. So what's the result? The result is that countable propositional logic and first order logic are consequence isomorphic. And this is quite a straightforward result, and it generalizes in some obvious ways. But I will mention the argument. I'm not going to prove it in detail, but I will mention the relatively simple argument that consequence isomorphism, and importantly, though, the isomorphism is not recursive. So let's just say what the result is in a little bit more detail. Maybe I should explain what countable propositional logic and countable first order logic are. What I mean by countable propositional logic is propositional logic with a countable infinity of sentence letters. So, P1, P2, P3, P4, and so on. And some countable infinity or some finite set of Boolean connectors. Maybe it's just disjunction, conjunction, and negation. Some expressively adequate set, or just a Sheffer stroke, if you like. And first order logic is similarly has a countably infinite vocabulary. So it's got a countable infinity of constants, A, B, C, D. It's got a countable infinity of predicate letters of every arity. And it's got a countable infinity of variables. And it's also got some expressively adequate set of Boolean connectives, maybe again conjunction, disjunction, and negation, or just the Sheffer stroke. You can take them to be the same connectives as propositional logic. Okay. Okay, so that's what I mean. The argument follows from three facts. If you have any two countable atomless Boolean algebras, then they're isomorphic. As a result, first-order logic's Lindemann-Tarski algebra is isomorphic to propositional logic's Lindemann-Tarski algebra. I'll give a little explainer in a second. I don't know how who exactly the audience is and what exactly everyone's logical background is. So I'm going to give a brief explainer on Lindemann-Tarski algebras on the next slide, just that we're on board. The little omegas there are just to indicate they're countably infinite. We're talking about countably infinite first-order logic and countably infinite propositional logic, and I've explained what that means, that the vocabulary is countably infinite. So the basic fact is that any two countably infinite, I should say, well, I mean, if they're atomless, they can't be finite, but any two countably infinite atomless Boolean algebras are isomorphic. The second fact is that both these logics are compact. That's to say, if gamma, I take most people will know what that is, but if gamma entails delta in one of the, if gamma entails delta, then a finite subset of gamma entails delta, and that will be true for both logics. And again, we've got the fact that each equivalence class in these Lindemann-Tarski algebras in sentences of FOL omega under FOL omega equivalence is countably infinite. Similarly for PL omega. So let me just give you a little explainer on Lindemann-Tarski algebras to make sure that everyone is on board. So the Lindemann-Tarski algebra of a logic consists of a domain of elements and two binary operations and one unary operation. The domain is just the sentences quotiented by logical equivalence. Whatever we're assuming we've got a consequence relation on that logic, on the sentences of that logic, and we quotient them by logical equivalence. So in the case of propositional logic, for example, P is in the same equivalence class as P and P, which is also the same equivalence class as P or P, and so on. Those are all logically equivalent, and therefore they are in the same equivalence class. And then what we do, we put a Boolean algebra structure on this domain. We can have conjunction or meet. We can have disjunction. And join, and then complementation, which we can just think of as negation. And these things are just defined by looking at the, for example, phi, and the equivalence class of phi and psi is the same as the equivalence class of phi and psi. Okay, so these are well defined because you can plug in any logical equivalence in here. So these are well-defined operations. So you do get a Boolean algebra, and that's known as the Lindemann-Tarski algebra of the logic. And it has a top element, namely the tautology, which is sometimes labeled T or 1. And if you've got a contradiction, then you've got a bottom element or 0 or bottom. Okay, so that's for anyone who's not familiar with Lindemann-Tarski algebras. Okay. Here's a little digression. So the result is, so just to go back to the result, the claim is that the countable infinite propositional logic and countably infinite first-order logic are consequence isomorphic. As far as implication goes, they cannot be distinguished. The Lindemann-Tarski algebras are isomorphic as Boolean algebras, and then that means that from the compactness and from fact 3, that means that they are consequence isomorphic. Okay, so there's a sort of more kind of mathematical question here, which you might ask. So there's a sense in which, if you use a sort of metaphor here, that they're equally roomy logics. They're just as capacious. They have just as much room within them as the other. So any argument form that you can model in PL omega, you can model in FOL omega, and vice versa. So a natural question here is whether there are logics that are sort of roomier than them, and have more room in them than proposition PL omega or FOL omega. FOL omega consequence embeds into SOL omega, for example. SOL omega is second-order logic. Okay, so if you have second-order logic in which you allow quantification over predicates or functions or both, then that and keep the all the other parts of first order logic. That's an extension of first order logic. A first order logic embeds is a sublogic of second order logic, and therefore clearly consequence embeds into second order logic because it's a sublogic of second order logic. So you might wonder where the first order logic is this result also applies to second order logic. Actually, second order logic does not consequence embed into first order logic, nor therefore into propositional logic. There's a sense in which it's just roomier in this sense. It can capture more argument forms than first order logic or propositional logic. And this is simply because of its non-compactness. So the technical question here is, okay, but is there some other countably infinite logic with countably infinite vocabulary that consequence into which every logic consequence embeds? Is there a sort of roomiest countable logic? Of course, for any countable, if there's going to be a very large logic in which you can consequence embed any countably infinite logic, you can the very sort of simple-minded approach would be to just take copies of all the consequence structures of a countably infinite logic, and there's some limited amount of those, and create a logic which just pastes together all these consequence structures. And that's going to be a very large logic, but you'll be able to do it. So is there a roomiest, though most capacious, countable logic into which all countable logics consequence embed? For example, could it be countably infinite second order logic? Could it be that second order logic, whatever argument form, whatever your initial countably infinite logic is, whatever your whatever language you speak, whatever implicational structure you put on your countably infinite language, could you consequently embed that into second order logic in such a way, that's to say, in such a way that preserves the implication structure of the original? Can you do that? This is a sort of technical question. The answer is no. And I've just got a paper with Felix Kemper, who that's just come out recently on this question on whether there is a countable omega universal logic, as we call it, logic into which you can omega universal, meaning you can embed any countably infinite logic in this sense of embedding, consequence embedding. Okay. Okay, so what's the corollary? Let's go back to our interest in formalization. What's the corollary for the first criterion? We said that the first criterion was to capture, the first criterion of good or acceptable formalization is to capture the implicational structure. And now let's see whether we wondered whether this trick that you can play with propositional logic could be played more generally. And the answer is yes, precisely from the fact that they're consequence isomorphic, right? So let's think about let's think about formalization map from E into first order logic. Suppose you formalize that using form. Then at the bottom here, you've got an arrow, that's a consequence isomorphism from FOL to propositional logic. That means that if you compose the formalization with consequence isomorphism, then you get a formalization function from E to propositional logic. That's going to do just as well as when it comes to capturing implicational structure as first order logic, right? So suppose you have two sentences of English, say A and B, A implies B, and then you capture that fact in first order logic. The formalization of A implies the formalization of B in first order logic. Then you follow through the consequence isomorphism. It will just follow that the formalization under that under J, the formalization of those initial sentences A and B in propositional logic, that the first one is going to entail the second one too, because you've got a perfect map here between FOL and PL, so you can't distinguish between them as far as capturing implication goes, because they are actually consequences. So the consequence for the corollary for the first criterion is that propositional logic and first order logic satisfy equally well. Okay, what about the other two criteria? So I said that the other two criteria are the grammatical one and the semantic proximity. Semantic proximity is not going to be able to discriminate between propositional logic and first order logic if you cache out semantic proximity in terms of truth conditions. So a kind of standard way of thinking about semantic proximity is to think of or to think of propositions is to think of them as sets of possible worlds. If you think of them as sets of the truth conditions as sets of possible worlds, and you think of that as capturing a sort of difference in truth conditions and difference in meaning as being reflected in difference in truth conditions, that's to say sets of possible worlds, then the fact that you have this consequence isomorphism between first order logic and propositional logic means that you cannot discriminate between propositional logic and first order logic in this way. Because whatever you map first order, whatever sets of possible worlds you map first order logic sentences to, you can do exactly the same for the equivalent propositional logic sentence, and you will do it in such a way that you will obey the same constraints. For example, if in propositional logic phi entails psi, if phi entails psi, then the image of these under the isomorphism J will also, J of phi will also entail J of psi. So that's to say, if phi is a narrower set of possible worlds than psi is, J of phi will be a narrower set of possible worlds than J of psi is. So you're not going to be able to distinguish and discriminate in these extensional terms between first order logic and propositional logic. So there might be other ways of understanding the semantic proximity constraint. The consequence isomorphism seems to have a strong mission for one very natural way of understanding it. Okay, what about the grammatical constraint? Things are a little bit more complicated here. But I think one can argue the following. For any given first order formalization, there's a PL formalization, a propositional logic formalization, that not only matches first order logic implicationally, but also by the propositional logician's lights meets the grammatical constraint. So let me say something about that. Let's look at the grammatical constraint. Okay. So let's just just elaborate on the earlier comments, earlier remarks about the grammatical criteria. Respecting grammatical form is usually a constraint on formalization. Even if it's not made explicit, it's usually implicit. So just to give the example, a similar kind of example to the one I gave earlier, we propositionally formalize it sunny as P rather than say P and Q or not Q, which is logically equivalent to it. Okay? Because what we're trying to do is we're trying to respect the grammatical form of it's sunny, and it's sunny just does not have a conjunction or a disjunction or a negation in any shape or form, it seems. Similarly, there's a planet, you would formalize that as there's an x such that px in first order logic, rather than the equivalent not for all x not px. Okay, that's the equivalent, but it doesn't look like there are any negations in the English. There's no universal quantifier in the English or equivalent. Therefore, the first formalization is more natural, much more natural than the second, even though they're logically equivalent. Again, given standard semantics, just assuming standard semantics. How to spell out this grammatical constraint, however, is on formalization is a tricky matter, right? Suppose that you come to your natural language sentences with a sort of wearing first order logic glasses, then you will see a particular kind of grammatical form. Whereas if you come to it wearing propositional glasses, you will see a different form. If you're a linguist who thinks about syntax, and you're in a particular kind of research program, you will see another logical grammatical form. And if you're another kind of linguist, in a different kind of research program in linguistics, you will see some yet further grammatical form. So the evaluation of grammatical form, I think, is very much in the eye of the beholder. I don't think there's a clear sense in which logical formalizations really can capture the grammatical form perfectly or in some sort of unbiased way. There is just a particular approach, a particular way of looking at an English sentence and what its grammar is. And it's hard to say what that grammar is because all those claims, any such claim is going to be very theoretically loaded. So it looks like we've got a dialectical standoff. right? If the evaluation of grammatical form is in the eye of the beholder, then it looks like you can't really compare, you can't really judge one formalization versus another on this criterion. You can't really say whether one is the correct one or the other one, whether it gets the grammatical structure right, because there are no sort of theory independent facts to get right, it seems. But hang on, that's a little fast, I think. I think in our particular case of interest, in our case study, there is actually a way to break the deadlock and to get some sort of more um, a criterion up and running, a way of understanding the criterion that can actually be such that can the two ways of thinking about the two logics can have different might be compared one to the other. Okay, so there might be some commensurability after all. I suggest. So let's think about a sentence like Bruin is a bear and Felix is a dog. Okay, so look, the first orderist, someone who accepts first order logic, and that's the way that they use that logic that they use to formalize. They see this as a conjunction. They would formalize this as BB wedge DF. Okay, so they see it as a conjunction with two conjuncts. The first conjunct is a predicate constant sentence, and the second one is another predicate constant sentence. So the grammatical form, the propositional form for the first order of that sentence is phi one wedge phi two, where phi one and phi two are propositionally atomic. There's some further structure to discern there according to the first orderist, but the overall structure is the main connective is a conjunction. So from the propositionalist, from the first orderist, point of view, the propositionalist who uses propositional logic to formalize sentences, she would be mistaken on her own terms if she assigned a different propositional structure to the English sentence than phi one and phi two, or some refinement that keeps the conjunction as the main operator. Okay, so look, so it seems given that they share the Boolean connectives, the truth functional connectives, and those are the ones the propositionalist uses and doesn't go beyond them, it seems reasonable for the first orderist to say, look, propositionalist, you've got it wrong, unless you recognize that the grammatical form of this original sentence, Bruin is a bear and Felix is a dog, is a conjunction. If you can't recognize that that is a conjunction, then that is clearly a mistake, which we can both agree on because we've both got the Boolean connectives in our arsenal of tools, of formalization tools. The propositionalist isn't going to agree with the next step that Bruin as a bear gets formalized as BB, big B, little b. They're not going to agree with that because the they don't recognize the subsentential form there given by the first orderist, but they should be able to agree that the overall form is a conjunction. Okay. So the idea is that the propositionalist formalization should be able to match the first orderist by matching any propositional complexity the first orderist discerns. Okay, that seems to be a sort of fair criterion that doesn't load the dice in favor of one rather than the other. It seems that both of them can accept this. Of course, the propositionalists will, in some cases, discern further grammatical structure than the first orderist and vice versa, but this further structure must be supplementary. Okay, so putting it a little bit more formally, suppose the first orderist formalizes sentence S as B of phi 1 up to phi n, where B is a Boolean combination. And phi 1 up to phi n are propositionally atomic. Suppose that is the case. For example, the first orderist might formalize Bruin as a bear and Fight as a dog as BB and DF, which is just a conjunction of these two formal sentences. Then the propositionalist formalization must be of the form B of psi 1 up to psi n, with psi 1 up to psi n are propositional formulas as well. They may or may not be atomic, but they've got to respect the fact that you've got the original form, the initial form, excuse me, is the Boolean use the Boolean combination B. I should stress that the constraint applies only to the overall propositional form of the sentence. So for example, if you consider for all x, fx, arrow gx, or ha, that might formalize all Frenchmen are generous or Albert is holy in first order logic. That should be taken by the propositional logician to be a disjunction, but you don't have to formalize the first disjunct as in any way containing the conditional, because that's internal to the first order form. That would be imposing the first orderist's own understanding of grammar on the propositionalist, whereas they can agree to the neutral ground of the proposition of the Boolean connectors. Okay. Okay, so just to summarize, respecting grammar is a constraint that is interpreted differently by different logicians, and the only dialectically acceptable constraint the first orderist can impose on the propositionalist seems to be this. If the first order formalization of S is B of phi 1 up to phi n, it will be the propositional Boolean operator and phi 1, phi n are propositionally atomic for the first orderist, then that's got to be the first orderist, the propositionalist must also see this as B of psi 1 up to psi n, with psi 1 to psi n are atomic or complex from propositional formulas. That seems to be the most, the fairest kind of test. If you have this grammatical constraint, then you can prove that propositional logic can match first order logic, both implicationally and grammatically. Okay. In fact, so if you kind of a twist on the argument that I gave previously, and this is the 2021 paper, that there is a map from first order logic to propositional logic that is a consequence isomorphism, and that also respects this grammatical constraint. So if you have if that's the interpretation of the grammatical constraint, then you can in fact do it in such a way as to meet that constraint as well. Okay, so let me just summarize where we are now. I've got another sort of 10 minutes or so, or quarter of an hour, and I'll end and take some questions if there are any. But let me just summarize where we've got to so far. What we're interested in is the nature of formalization. We're trying to work out what it is for a formalization, that's to say a map from the sentences of English or a natural language into the sentences of formal language to be a good formalization or an acceptable formalization. We've seen that there are better or worse ways of doing that. What criteria guide that process? I've cited three. I've cited capturing implication, I cited respecting grammar, and I cited semantic proximity. And then we looked at the case study of propositional logic versus first order logic. And I argued, relying on some technical results, that actually, despite what you might think, propositional logic does much better than you would imagine. It can capture implication just as well as first order logic does. It looks like it can capture the semantic constraint or the semantic criterion just as well as first order logic does, assuming we understand it a particular way. And semantic proximity doesn't look like it's going to drive a wedge between propositional logic and first order logic either. Okay, so that's where we've got to. Let's see what happens next. What do we do next? How do we react to these facts? Okay, so one reaction is to learn to live with this result. That propositional logic is, in fact, despite what we all thought, is just as good a formalization tool as first order logic. That would be one reaction. I think that's a very extreme reaction, quite a radical reaction. I don't think it's the right approach. It goes against very established practice. Think of the great formalizing drives of Frege, Hilbert, and others. Those could not have happened in propositional logic. It seems integral, essential to good formalization, to understanding, to capturing the logical form of mathematical sentences, that we formalize them in first order logic, predicate logic, or some other logic at least, but that logic, predicate logic, does a better job. First order logic does a better job than propositional logic. Okay, so let's set aside this first reaction, but as I say, it is a possible reaction. A second reaction is that maybe we've misapplied the grammatical criteria. Maybe we should just insist that logic should articulate grammatical structure beyond the sentential. It should dig into the structure of the sentence in the way that propositional logic does not. Okay. And okay, maybe if you're convinced, if your opponent, your dialectical opponent, is a propositionalist, then you're not going to be able to convince them that logic, that a good formalization should do that, because that precisely goes against their view. So you're counter-asserting their claim that you only need propositional formalizations to do the job. But maybe if just being dialectically uncompelling to them isn't the same as being wrong. Maybe it's just right to understand the grammatical criterion in such a way that favors first-order logic, but but nonetheless, you cannot um, convince a committed propositionalist of this fact. Okay. Nonetheless, this might be correct. Nonetheless, it remains difficult to see where the preference for a non-propositional formalization comes from. Right. Even though that is the case, I mean, it seems odd that you should not be able to have the resources to show that propositionalism is somehow limited by it would seem odd, it would seem unsatisfactory if, as a first orderist, the only criteria you could come up with to favor your own formalization were criteria that the propositionalist could meet just as well. That would be a sort of unsatisfactory situation. So I want to explore a third option, that there's a missing criterion. There's something else that we've forgotten about, or that I have forgotten about, and I want to explore what that might be. Now, perhaps this is something you thought of all along, and I was being slow, but I think it's instructive to get to it from where we started. And this is the idea that formalization is a map a um, in another sense than the one the earliest sense. Here's the missing criterion, I think. The missing criterion is epistemic. More precisely, L1 formalizations are superior to L2 formalizations if the former allow us to discern facts about validity better than the latter. Okay, so the other criteria were not epistemic. So the first criterion was capturing implication, and capturing implication does not look like it's epistemic. You've got an implicational structure on the one hand, and what you're trying to do is over here on the left, and you're trying to capture it with an implicational structure over here on the right. Whether anyone is able to know it or not, what you're trying to do is you're just trying to match one structure with another. Similarly, respecting grammatical form doesn't look like it. Yes, I believe there's a question. Do you want to ask it now, or do you want to come back to it later?
Yeah,
I see.
we can for question we can just leave after your main lecture.
Okay. I don't have very long to go, so we can take the question in a bit. Yeah. Um, I'll continue then. The so that's and the semantic proximity is a criterion that has to do with semantics and doesn't look like it's epistemic either. Okay. So judged by the epistemic criterion, first order logic is superior to propositional logic, both in principle and in practice, because it's a better tool, epistemic tool, with which to formalize. We are able to discern the logical structure of English or technical fragment thereof using a first order logic um, in a superior way to how we can do it with propositional logic. Not in every case, but in general. So not in all contexts, but in general. Okay. So what does this imply? Suppose that formalization is epistemically constrained in the way that I suggested. Does that mean that logical consequence is also epistemically constrained? Okay. If it's sort of the nature of logical of formalization to respect this epistemic criterion, um, does that mean that logical consequence is somehow epistemically constrained? Because remember, at the start of the talk, I explained that on the standard formal approach, the standard contemporary approach, the analysis um, of logical consequence in English, logical validity, is analyzed in terms of a formal validity. And you might worry that if formal validity is an epistemic fact, epistemically constrained, that also means that logical consequence in English is also epistemically constrained. So just think about the initial biconditional. For all natural language statements, little s, and sets of statements, big S, S logically entails that big S logically entails that little s, if and only if the formalization in L of big S entails in L the formalization in L of little s. So one picture is that the right-hand side has priority. That in some sense, what we have an analysis here in which the right-hand side has priority. In some sense, the facts about the formal language constitute the facts about English, logical entailment in English. And I think this is the view that someone like Bertrand Russell had. That Bertrand Russell had at the start of at one point in his career, at the start of the 20th century. He did think that the job of philosophical logic was to somehow expose, analyze in some fairly literal sense, the actual structure of these propositions in such a way that the right-hand facts about the logical form were the ones that were actually underlying in some literal sense the left-hand side ones the surface facts that you see in English when you understand that one sentence entails another. But I find that a difficult picture to accept, an unpalatable picture, because it's hard to accept the idea that L facts really constitute the relation of logical consequence among E sentences. It's hard to think that what's going on, somehow the formal language facts are the ones that are really underpinning, they're the ones that actually constitute, ground the English validity. You might explore that further, but I think that's an unappealing picture. On the second picture, the right-hand side captures the left-hand side, but it doesn't have priority in a sense. It just represents, it captures rather than constitutes. Okay, so that I think is a much more appealing picture. And this leads me to my last slide. And I think we can I said we can see that formalization is a map in another sense. So there's at the start of the talk, I said that formalization is a map in the mathematical sense that it's a function from the set of senses of English, the set of senses of a logic. But in a sort of play on words, I think it's a map also in the metaphorical sense of in the everyday sense of a map. It's akin to the relationship of logic to logical consequence is akin to the relationship of a map to some territory that it describes. So you've got a map, which may be a map of China, and it describes China. What would a perfect map look like? At least one of the things that it does, it preserves distances, it preserves directions. Under this analogy, the correct logic for capturing logical consequence is akin to a perfect map. Okay, so that's how I suggest we should think of the epistemic criterion that's constraints formalization. So suppose that M is a perfect map of China. You want to get facts such as this one right. Wuhan is west of Shanghai, if and only if M depicts Wuhan, excuse me, that should be Wuhan, there's a typo there, as west of Shanghai. Okay? But there's no sense in which the right-hand side constitutes the left-hand side. Right? The map just depicts these directions, in this particular case, or distances and some others. And the job of the right-hand side is to capture the left-hand side, but it doesn't constitute the right-hand side. But also, importantly, a perfect map does more than encode the orientation of some places vis-a-vis others. It does so in a way that's readable by the map's users. A map has to be direction and distance preserving, of course, but it's also going to be readable by the user. It's got to be a usable map. And my suggestion is that this is analogous to logic's encoding of implication relations. A logic, when in this application of capturing consequence, of trying to understand what it is for some sentences to imply another in natural language, including technical parts, has to be able to be usable. So there has to be an epistemic component. Okay, and that helps us to see why the fourth criterion is needed, right? Because think of formalization as a map. Okay, so I'm just going to just re-summarize very briefly the talk. We've looked at some. I said that formalization is the key first step in the contemporary account of what it is of logical validity. I focused on formalization. I tried to get clear on what it is and what guides it. We looked at three criteria. I argued that the criteria don't distinguish between propositional logic and first order logic, and that seems to be problematic. And therefore, I suggested a fourth criterion, an epistemic criterion, which does distinguish between them. Maybe we could have got there faster. I don't think the literature has appreciated this enough. I certainly had not appreciated it before going down this road. And that's the end of my talk. Thank you very much.